So please go at the back there. There's some kids here. Kids, I suppose this is Mazda. So please. Okay, thank you.
Okay, I think we're up and running. We're all back, wonderful. So we're going to start the second part of this symposium with a talk from Maria Jesus Pascual Lopez, who is from Spain and is going to be talking to us about nanoemulsions of plant essential oils as aid component. Maria, over to you.
I'm really glad to be here to present our work on emulsions of plant essential oils as acid repellents in the International Conference on Pesticidal Plants. My group has been working on the use of essential oils as natural insecticides for quite a number of years, although the formulation as an emulsion is a new field research we are starting. Therefore, I will present here some preliminary work that hopefully will be a more complete paper we are preparing to submit for the special issue of Industrial Crops that is going to get with occasion of this meeting. In spite of plant volatiles having insect repellent properties, its use at the commercial level in agriculture is low so far. The very old acid romantic body attacks all kinds of cereals and causes direct damages by leaf contortion and indirect damages by transmission of the barley yellow draft virus. It is expected that with climate change, a more severe attack of the pest will be on the crops because alates will be laid earlier to the fields because of more winter survival. Active females produce colonies with a high number of individuals. Robalosicum valley was cultured under controlled conditions on bunkers of barley plants to produce the insects required for the biosales. Third instar nymph of paddy produced for the biosale that consisted in a choice biosale offering the insects least treated and untreated with the product into biosales. One with an opening covered with mesh. We call this ventilated biosale, and another with the lid without the opening. This was in this device to increase the effect of the volatiles and to see the different effects. After 24 hours, the number of insects in each of the leaves was counted and the repellency index was computed together with the mortality. We tested a group of essential oils and pure compounds. The essential oils that were tested included species of the Umbelliferae, such as aniseed, Pimpinella anisum, coriander, Coriandrum sativum, fennel, Phloeniculum vulgare. We included as well 2 species of the labiates, basil, Othimum basilicum, and 2 mint species, Mentha piperita, peppermint, and pennyroyal Mentha puletum. Also, lemongrass, Timopogum flexuosus, and lemon essential oil from distillation of fruits and from cold extraction of organic fruits. And pine oil was included too. The pure compounds consisted of a group of phenylpropanoids such as arsenetol and estragol, and also different monoterpenoids such as monoterpenic ketones, carbon, perchon, tenchon, pulegon, methone. Also, the monoterpenic aldate, citral, the monoterpenic alcohols, geraniol, linalol, menthol, and other alcohols like farnesol and cis-hexanol, on monoterpenic hydrocarbons such as limonene and betapenene, and other compounds such as cis-hasmone, cis-salicylate were included too. The first screening of products was done by application of the products in acetone solution. But after the active products were selected, then we formulated the oils as nanoemulsions. In the way of nanoemulsions, we used an ultrasound with a processor for 10 minutes and we mainly as a surfactant. In this way, we obtained particles of oil within the emulsion that were in the nano scale. That meant that were around 100 nanometers in size. Next slide. Well, it seems that it doesn't want to move from this slide, but then okay, so now it's working. So here we have the results for the essential oils, and we can see here the values of the repellent index. There were 3 oils that had activity on the acids, were aniseed, peppermint, and lemongrass. In the first case, with aniseed and peppermint, there was a difference between the results of the ventilated and airtight biocides. A more pronounced effect was produced by the effects of the volatiles in both cases. However, for lemongrass, we have a similar activity between the 2 types of biocides. There was some mortality too with coriander oil, with lemon from distillation, and with coriander and with aniseed. Here we have the results of the compounds, and we can see that there were some of them that were toxic to the insects, that included mainly transanethol, methone, and menthol. In these cases, the mortality ranged from 46 to 89% of mortality, and therefore the repellency index could not be computed. There were other cases in which we had a very clear effect of repellency. For instance, with citral, with limonene, with geraniol, with farnesol, and also with linalol, estragol, cis-ethanol, and cis-hasmone. In these cases, there was not much difference between the results in both types of biocides. There was also some mortality, but the values were not very high. The main compound of aniseed is transanethol. Transanethol is the phenylpropanoid that was found in 96.9% in the oil. And this is the effect that it was doing to the insect. It produced mortality, and in some cases, some hemolymph exudates were observed. The main compound of zero-common lemongrass is citral. Citral was found in 79.7% of the oil, and it included geraniol, the monoterpenic aldehyde, and cis-isomer-neranol, so it's a mixture of both. This compound is clearly a repellent, as it was shown in the biocides. Peppermint oil consists of menthol, the monoterpenic alcohol in 40.4%, and menthol in 23.5%. Peppermint was quite active, and here we can see the result of the nanoemulsion that was formulated, as I already explained, and we sprayed that with the computer controlled spraying apparatus, and here we can see a good result in terms of increasing values of repellent index with increasing doses. There was you see in the graph below an histogram that represents the mortality also and settlement. With increasing doses, there was as well more mortality and therefore less settlement. Here we can see other compound that is carbon, a monotonic ketone, that was interesting because in addition to having repellency, it produced an increase in insect mobility. You can see here that establishment was quite low in spite of the insects being alive. An increased more mobility is useful for pest control because the insects will be more exposed to other chemical treatments or biological control agents. There were compounds very active like cis-carbon that had at 0.02 microliters per square centimeters. It had a repellency index value of 60. Petit Royal contained different composition with 82.4% of poulegone. That this oil was not very active, but when poulegone was tested alone, it was more active, producing toxicity in the airtight bioshell and repellency in the ventilated bioshell. Then we studied the effect of particle sizes in the emulsion on the activity. We can see here, we characterize the emulsion using a synthesizer that measures particle size and average volume, diameter, 50% and 90% percentile distributions, and the polydispersity index. We can see here that in a nanomulsion, we have particle with 99 nanometers, and the repellency index value was 66, while emulsions having 800 or 3,000 nanometers on average were not active. This was with residual 2% emulsion. The temperature response was important in activity too. The 1% nanomulsion of aerosol stored at 4 degrees kept the activity after 3 months. As we can see, the repellent index value of 77, while it was not active if it was stored at 25 degrees. Here, we can see in the graph particle size distribution was also associated with smaller particle sizes of the active emulsion. Transcendental was always stable, formulated in a nanomulsion, even in a concentrated manner. Here you can see 10% nanomulsion, and there is not a visual difference in the emulsions during 30 days or even. This was not the case for citral. Citral was better stored at 25 degrees instead of 4 degrees, but what we have is after 15 days, a clear separation in 2 layers, while if it was at 25 degrees, a clear stable nanoemulsion, while after 30 days, the particles started to flocculate on correlates to give a milky appearance. We are starting to use other surfactants such as lecithins. Lecithins are considered as basic substances and therefore can be used in the formulation of plant protection products. Also, they are authorized in organic agriculture. If we use lecithin instead of 280 for the formulations, we have obtained here that the 1% citral nanomulsion kept its activity after 2 months of storage. Here we see the 93 of repellent index in comparison with 30. In addition to associated with smaller particle sizes, we have as well a zeta potential value much larger. Zeta potential is a value that indicates the repulsive forces of the oil droplet particles in the motion. By using a surfactant, it covers the bioactive and produces more repulsive forces, and if we get values of theta potential less than -30 or more than +30, the emulsion is more stable. We are starting to use another stabilizer to glycerol. So if we add, in addition to lecithin, glycerol, we have a further reduction in theta potential values in spite of having larger particle sizes, and there is not a significant change in the value of the activity. As I said, these are preliminary results. There is still some work in progress with the products. We have to calculate the repellent doses 50 and 90, the lethal doses 50 and 90. Also, to study the response in terms of repellency index of spraying different doses of the nanoemulsions with the computer-controlled spraying apparatus. And finally, we are characterizing the emulsions formulated alone with lecithin or with lecithin and glycerol, and compare the results in terms of the repellent activity against the acids and in terms of its characterization. And I thank you for your attention.
We're a little bit short of time. If there's one very quick question for Maria. Anyone got a quick question for Maria? I think you should take that. Oh, we have one. Make it very quick, though, please. Quick question.
What equipment do you use to produce those nano emulsions?
You can produce nanoemulsion by ultrasounds. So with a liquid processor, ultrasounds, you can get particles this small. Also, you can make this emulsion by kind of, say, very high speed stirring. And then you can get by physical mechanism the same effect.
Okay, thank you very much indeed, Maria. I'm sure you'll get much more interest after you've had a chance to digest all the fascinating things that you've talked about. These two. And next we have Angela Kindi, who's from the Nelson Mandela African Institute of Science and Technology in Arusha, and she's going to be talking to us about the efficacy of pesticide plants for field crops management. And I know this work from around Arusha, so the floor is yours, Angela. I'll be giving you a warning in 5 minutes. Okay, you've got 15. All right, thank you.
I am thankful for the opportunity to present on the efficacy of the set of plants for crop management. As I said, my name is Angela. So, use of pesticide plants is here explained into 3 main aspects. One is the on-station use of on-station assessment of pesticide plants on cowpea production. The second aspect is the participation of farmers to assess the efficacy of pesticide plants in their crops. And the third one is the use of the fusel, particularly to crop protection, and this is done in a farmer research network approach. So the first aspect is an on-station trial in which simple extraction of 6 species of plants was done using 0.1% soap and just water. And these concentrations were agreed 0.1, 1, and 10 in 4 replications. And the extract was sprayed into the field on a weekly basis and for 10 weeks during the growth of the cowpea. Generally, the fossil modeling went best, and this is explained in 3 or 4 aspects. First of all, the ability of treatments to reduce damage to the crops. It shows here that the fossil modeling works best to control damage. The result goes on seen between the negative and positive control. Of course, there's high damage in the negative control, and also very low damage in the positive control, which is the synthetic pesticide, but much appreciated with the frozen jelly, which has shown a great efficacy in controlling damage. Another thing is the effect of the treatment of beneficial insects. These are like bed beetles, robber flies, hoverfly, lacewings, and spiders, and so on. And it is seen just in the graph how synthetic pesticide reduces a considerable number of beneficial insects as compared to other pesticide plants, and also compared to the negative control, showing that there's much less harm to beneficial insects when using pesticide plants as compared to when using synthetic pesticides. Another observation is on the yield, effects of the treatments on the yield. It shows in the yellow line showing the controls, negative control having really low yield, and positive control having the highest yield. This entails ability of the synthetic pesticides to control damage, and that's why there's high yield. But again, there's good observation in the use of in the frozen jelly showing also higher yield, the grain color showing very high yield in the frozen jelly, and of course with the other pesticide plants. Here we think that the frozen jelly has much more contribution on yield apart from controlling insects, because we know that it's ready, it fixes nitrogen. But then this was a spray, so looks like spray has much more advantage, and I think this is a point for future research of the mechanisms actually on how a spray can also contribute to growth parameters of the plant. Again, another observation is that concentration matters in improving yield, because the higher the concentration shows here that even the yield is increasing. Another aspect is farmers' involvement in assessing the efficacy of these plants. In this case, only one concentration, which is 10%, was used, which is of course the best one, and farmers had a chance to receive a one-day training on how to prepare the products itself. And the second picture here shows the farmers, the father and the son, trying to prepare their own extracts to spray on the next day. And farmers were grouped, 20 farmers having monocropped farms and 20 farmers having maize and beans intercropped. And each one was provided by 3 species out of 6, of course, with 2 controls, negative and positive control, which is the pesticide. At some point, farmers were also involved in ranking or assessing which is the best plot in terms of treatments. And of course, the researchers had also a chance to do some other collection of data. Again, it shows how the process of again was best on the side of pests, and also how pesticide plants have the ability to retain beneficial insects. This one side of the graph shows predators and one side shows pests. So it also shows that the results from this experiment coincides with some other results which show how best pesticide plants work as compared to the negative control. In the ranking, farmers had a chance to rank 1 up to 5. 1, which means the best plot, a plot which is well controlled, and 5, the worst plot. And the ranking is shown in some purple triangle, farmers rank. Yield is shown in red dots, and extent of damage in blue blocks. It shows how farmers' observation coincides with the analysis from the data collected, which means if a plot is ranked very low, means it is the best, and it shows it has higher yield. There's one exception in Lantana, which is Lantana Camara, which is rated not good, but still having a higher aspect, number of predators are much more. The abundance is higher in the side of grass control plots as compared to synthetic pesticides. And when comparing monocrop and intercrop area, it just shows that there's no very much difference in terms of pests, insect numbers, but then it shows that the abundance of beneficial insects or predatory species is higher in the intercrop than monocrop, entailing that biodiversity in an area can have a lot of insects, many of these being beneficial ones. An example is one here. This one picture having a purple flower is actually a flower of the Fossia Bodini, covering an insect which is a wild species of bee. Another picture is actually a leaf of maize having also another beneficial insect. In terms of damage, high damage is in the monocrop area and in intercrop, as well yield, which is higher in the monocrop than in the intercrop. So farmers can evaluate, and this information is quite important and also very useful in research. And they can give very nice feedbacks. For example, one feedback from the experiment is that the Fossia is the most perfect one, is preferred, and it can easily grow. And taking off from there, farmer research network is something that has been very useful. And based on the comment, then farmers had a chance to receive a one-day workshop also, discussing how important the cycle plants are, and afterwards receiving seeds in order to take off from there. Again, planting the Fossia Bodini. Here is the nursery that contains the Fossia Bodini. This is one of the lead farmers who has planted and is ready to give it to the neighbors to plant, so that use of the set of plants starts from there. At the moment, there are over 100 farmers who have formed different groups and so different networks, but a very good interest is being built in the society. A lot of NGOs think of using and propagating the use of the set of plants, especially the Fossia, and also in the schools. Thank you very much, and I'd like to kindly acknowledge the University of Greenwich from Professors Berman and Steele, and Phil, Nelson Mandela, University of Luana, and the Royal Women's Company. Thank you very much.
That's a very nice talk, Angela. Thank you very much. And you're clearly showing that the value of these plants when considering beneficial insects. We have a couple of minutes for questions, if anyone has a question for Angela. I'll kick off then. One thing that crosses my mind is when you demonstrate that these plant materials have reduced impacts, not no impacts of course, reduced impacts on beneficial insects, how do the farmers understand that? How do the farmers interpret that? Do they know what beneficial insects are?
Thank you for the question. It is really complicated at the moment for farmers to know which is the beneficial and which is the best. Basically, a normal farmer knows that every insect is just a pest. I think this is also an area that we will have to consider and try to let people understand which is the best and which is beneficial. Because the majority of farmers know that bees are bad because they sting. They make them some pains.
Excellent, thank you very much. Do you have any other questions for Angela? No? Okay, well, Angela, thank you very much indeed. Very nice talk. Next up, we have Edwin He's got to pronounce it properly. I'm going to try this. I'm going to get it right. Margarita. Fantastic. Okay, so next up we have Edwin Margarita. I'll just, now while I'm doing this, I'm going to do a bit of gap filling. While I'm telling you all that Oh, it's here already. Edwin, that's not the correct one. We appear to have uploaded the wrong talk, so we'll be as quick as we can. Sorry about this, everybody. While I'm doing this, I'll try and multi-scan and inform you about the fact that we unfortunately have lost one or two people in the afternoon. And we have the understanding that there might be one or two people who have turned up with talks who don't yet have a slot. If that is the case, then if you during lunch could go and speak with Prof. Steve Belname, continuing to do a lot of the unseen work that keeps this conference going. If you could go and see Steve Belname, if you have a talk that you would like to give, we'll see if we can find you a spot this afternoon. Okay, thanks. So without any further ado, Edwin Rajawita on Plutella and Brevet O'Reilly and the effects of climate extracts. Thank you.
Thank you. Good morning. I'm going to present on station on farm evaluation of aqueous plant extracts against Plutella, Xylostella, and Brevicola and Brassicae in brassica production. An experiment which was conducted at the University of Zimbabwe and in Marondera, that is in Shosha, 120 kilometers from Harare. Plants was trained in vegetable production in the sub-Saharan Africa, and at the same time, vegetables are consumed widely in Zimbabwe. Plants are also nutrition security, but there's a great damage of vegetables by pests like aphids and diamond black moth. But normally farmers would respond by using synthetic pesticides, but these synthetic pesticides may pose a threat to human and the environment. But it was also noted that farmers are now opting for affordable treatment options, and also it was also again noted that farmers, researchers in some agrochemical industry, they are now focusing on alternatives to chemical pesticides, and these alternatives include the use of pesticide or plants. There's also clear evidence that farmers are already using pesticide or plants, but there is a lack of reliable information, and this unreliable information is contributing to the limited adoption of these pesticide or plants. And also there's a lot of promotion of these plant products by development agents like the NGOs without scientific rigor. And there's no clear indication of those following aspects, which includes effectiveness and also application on which crops, and also the application rates, and also these plant products are also they safe to both humans and the environment. Hence, these issues need to be investigated. And the objective of my research was to evaluate the efficacy of selected pesticide or plants against vegetable pests. Now, on my methodology, these are the indigenous plant material that were investigated for the Obrania madagascarensis, which is called Mucherekes in our local language, Shona, or snake bean. And also, there's also Maroa edulis, which is called bushberry, and it's called Kachunguru, or Sozwe in our local Zimbabwean languages. Two experiments were conducted. One was on station at the University of Zimbabwe, and the other one was in on farm at Marondera. RCBT was used broadside 2.5 1 meter with an inner production of 0.3 meters with growth of 0.9 meters. And the crude extracts from these pesticide plants we found it using the traditional methods which are demonstrated here, using our pesto in water, and also mixing with water overnight, and then mixed with the surfactant, and then it was passed through sealed with different sizes so that it can be easily sprayed when you spray. These are the after some treatments, I got this. That insect I didn't put it, it was just a photo. And also you are seeing maybe the differences in the color of our vegetable leaves after spray. Some, for example, Bogania madagascarensis, it makes the vegetables look a bit unpleasant. So on my selected results, I started with a number of concentrations from 3% to 20%. These concentrations were based by the farmers' experience. Farmers will tell you a wide range of these concentrations. Hence, we first tested these concentrations, which may be a wide range. And I observed that under Merwa age release, in most cases, there were no significant differences between 5, 10, 15, and 20%. And also in Organia madagascarensis, there were no significant differences in most cases between 15 and 20%. Hence, the 15 and 20% for Organia madagascarensis and the 5 and 10% were further evaluated other on experiments, and generally there were no significant differences among those treatments. Again, on the diamond-back mode, a similar study was conducted, and it was also observed again that generally there were no significant differences between the 5, 10, 15, and 20% for Merwa age release, and 10 and 15% for Bogania madagascarensis. And further studies were conducted under on-farm conditions in Marondera, and it was again observed that there were no significant differences between the 5 and 10% for Merwa and 15 and 20% for Bogania. On the selected results, there were again no significant differences on the plant extracts, although they were a bit, they were having a bit lower yield than the treated control. They significantly differ from the untreated control for both the cabbage and the herb. On my discussion, we observed that there were no significant differences between 5 and 10, and there were no significant differences between 15 and 20 for Bogania and Merwa age respectively. And also we observed that those treated with plant extracts had significantly higher cabbage and herb yield compared to the untreated control. Hence, there is a potential of local plant extract sprays for pest management on a smaller order farm, and also in organic vegetable production. Again, for farmers can use 5% volume, that is about 50 grams per liter for Merwa age release, and 15%, that's about 150 grams per liter for Organia madagascarensis. But there's a need for future work, like repeat the trials may be assessing the impact of frequent of application, and also extract the 15% of Organia madagascarensis may be a bit higher. They can be a bit higher, maybe given a situation that everyone in the community is using these pesticide or plants. We may have challenges in terms of conserving the natural resources. Otherwise, I thank you for listening.
You've left us plenty of time for questions on this talk. If anybody has a burning question, does anybody have a question? Yes, Murray.
I wanted to know the effect on the aphids was mortality or prevalency, or which effect?
Okay, I can answer that one. There was I think there was an issue of repellent, although it was difficult to tell, but there was an issue of maybe killing by direct contact. Because when you spray, for example, Bulgaria, you see that all those aphids, they'll be actually sticking to the leaf. Yeah, that was I observed. Although there is maybe some work, maybe through Stevenson Institute, maybe to see maybe the active ingredients which are actually active in maybe against these pests.
I don't want to kind of preempt my talk tomorrow, but I will talk a bit about the chemistry of Murua egilis, which might enlighten us a little bit. I do know that Bulgaria madagascariensis contains quite high levels of saponins in those pod extracts, which might have some kind of soapy kind of saponinish kind of effect. We know that they have kind of direct toxic effects as well. That sticking might be because of the saponins in the extracts as well. One of the questions I have is regarding the concentrations. It seemed that 5% was as good as 20%. Yet 20% obviously is a very difficult extract to make because you almost reconstitute the fresh weight of the leaf. Do you have any plans to look at lower concentrations? I mean, how low do you think you could go with some of these? Because 5% is as effective as 20. Could you go down to 0.1% possibly?
Yeah, I think there may be some improvements. Because I think usually mainly on the extraction method. This extraction method was not very effective. Like maybe we may need some kind of electronic grinders which can maybe increase the surface area of the material. Because that one is just, the traditional way of doing things. But I think if we can increase, if we can improve on the extraction method, I think we can get the best results. We can actually reduce the concentration.
Yeah, well, I think one of the problems you face when you're trying to extract 20% extracts of dry plant material is that plant material has the capacity to essentially reabsorb all the water that it once had before you even actually get any spare liquid. We have a question here.
Okay, thank you for the interesting presentation. What I wanted to know is during your extraction process, how long did you wait before you could use your extract? I might miss that one. At the same time, I think maybe it would also be interesting to observe the different efficacy, should I say, of the extracts maybe stored over different periods of time. Maybe linked to the previous presenters, what I seem to be realizing maybe is that when you use these extracts and with the setting that you harvested the planting material, maybe also highlighted during the panel presentation, where were they harvested and what was the time in terms of harvesting? Would there be also an interest also in terms of looking at the different seasons when these plants are produced in terms of also producing the same effect? Or are they always the season this plant extraction?
Okay, thank you. In terms of timings, after 24 hours. After 24 hours. Then in terms of season, all those plants like the Bulgaria and Murua egilis, they just have their fruits maybe at a specific time of the year. Like in our conditions, then maybe August, September, November, they won't be having many fruits. So I think maybe it's an issue of to do with maybe preservation of those plant materials, but they are not perennial. They just have their fruits only on a seasonal basis. Then after that, we won't be getting any. So maybe we can need to work on how can we preserve those plant materials so that they can be used in future times.
Thanks. We've got time for two more quick questions. We've got one here, ready to go, and one at the back, I think.
Okay, thank you very much again for your presentation. My question really is on dimethoate. What's the standard for diamond black moth? I mean, were there any specific reasons why you choose that product? Whilst it is a broad spectrum pesticide that maybe not the best for DBM. Why I'm raising this question is the inferences that will draw at the end of the day. Thank you.
There was no special reason why to choose the method, but again, it is the one which is most used by our farmers against TPM.
It's worth pointing out, actually, while the last question gets ready to ask, we're going to have to move on. It's worth bearing in mind that dimethoate, of course, is now one of the most recently banned pesticides in the European Union. I think Kenya has already banned it because, of course, the risk of dimethoate getting onto produce that's leaving Kenya and then arriving in Europe and being sent back. So that's an interesting point to raise, actually, dimethoate. Right, one last question, sorry, we are going to have to move on to the next talk. There'll be plenty of time over lunch to discuss any further things with Edward. One last question.
Yeah, thank you very much for the good presentation. I want to ask just a small follow-up question on the concentration you are recommending for making these botanical pesticides. My worry is that concentration of chemical ingredients in medicinal plants is weather and geographical area sensitive. So your recommendation might work only for the area whereby you harvested the medicinal plants, and maybe it can fail to work in the other areas. What is your opinion on this?
I think my opinion is like what you said, that maybe it can work best in Maronda where we took those plant materials and may not work maybe in other areas. But I think we may need to embrace some concepts like what is presented by Prof. Eastman, like maybe trying to mix certain plant species so that we can do away with those variations. Thank you.
Okay, thanks very much indeed, Edwin. Great talk. Plenty of time to talk to Edwin afterwards for those who are interested, of course. So I'd now like to ask Happy to the stage, please. Is Happy here? Yes? Which I'm sure I can before she gets to the stage. Right, so Happy Dowdy is going to be talking about the effects of selective pesticides on controlled sesame. 15 minutes, and I'll give you a reminder in 5.
Good afternoon. Thanks, again for this opportunity. I'm here to present the effect of selected pesticides on the control of sesame breeding. As I said, my name is Happy Daudi from Tanzania. Just to show you where I came from and where my work done is in the my work will be concentrated in this southern part of Tanzania, Lindi, Tunduru, and Mtwara. Just to give you an introduction, what is the importance of sesame crop? As we know, this is a source of high oil. It's used for industrial foods, and also this oil also used for massaging and in cosmetics. Actually, this crop faces many problems, especially biotic and abiotic. You can see this is the diseases from the sesame crop. This goes to viral disease. This is the farad and this is the leaf curl. Also, we have another problem which caused by waterlogging, which is the stem rot. But also, we have a problem in insect pests like sesame webworm. This is the effect of sesame webworm. Also, we have a big problem in sesame free beetle, and this is the effect of sesame free beetle. And we use the different measures to control sesame free beetle. For now, farmers use their lots, synthesized chemicals to control sesame free beetle. But also we hope to, if we have cost resistance varieties, this can be a good measure because it's cost effective and environmental friendly. But up to now, we don't have that resistance varieties. Thus, we hope the use of botanicals can be the best alternative control measure against sesame free beetle. And this is the botanicals which I'm going to talk with. In young language, this we call it chinyenye, that is the snake beans, and this one is mukuna. And this is the synthetic one. We use it is carrot and gaucho. This is the seed treatment. We treat seeds before planting. That's gaucho. And this is the effect of sesame free beetle. This is the Bengalese stage, the one in the left. In this stage, you can lose up to 100% yield. And this is the stage also, this is affected by the adult sesame free beetle, and this one is affected by the larva. They suck in the roots, and you see the leaves with. In our study, first we conducted the survey in order to see which plants first are used in this area, and we observed for Luangwa and Nachingwea, mainly they use mukuna, and for Tunduru, they use snake beans. That's why we opted in our study to use mukuna and snake beans. Mukuna and snake beans was applied in, this is supposed to be 1 kg in 5 liters of water. Carrots, the rate was 5 liters in 1 liter of water, and the gaucho, the rate is 10 mils in 1 kg of seeds. But if it's in a powder form, you can use also 10 grams in 1 kg, in 1 kg of seeds. Also, in our trial, we used the fertilizer. We used the urea fertilizer because from the observation or from our experiments, the previous experiments, we observed that if we use this fertilizer, you can boost the yield, and if you boost the yield, sometimes you can escape the effect of a free beetle. And the variety used was Ziada 94. The results. In 2006, we did only the trial with gaucho and fertilizer. We did the one of local varieties. We tried to see if we use the local varieties and if we use improved varieties, there is any difference in yield. Because the effect of sesame free beetle always we see in the sesame yield. So that's why we took only yield. So after observation, we see that if we use improved varieties together with gaucho, you can see the yield increased. And if we use the local varieties, the yield will be local compared to the improved varieties. After that, also we try to do the other experiments to combine many treatments in order to see the effect of it in sesame yield. In this experiment, there were control. In this we didn't use any pesticides. Also, there were the block which we used only chinyere and fertilizer. Also, there are another block we used only chinyere, the other one we used only fertilizer, and then other one we used carrot, and the other one we used carrot and fertilizer. The other one we used the gaucho and fertilizer. This one supposed to be carrot and fertilizer. I think there is typing error. This one is carrot, this gaucho and fertilizer, this one gaucho only. As you can see from the results, the one which we used the carrot and fertilizer gave us high yield. Also, the one which you use the carrot also gave us high yield, not compared to others which we use maybe chinyere, which is this is the snake beans, or the one which we use the gaucho. This is the reason why if you treat the seed with gaucho, you can prevent the effect of free beetle only for 4 weeks. After that, if that is free, maybe this is the second time to use. You are supposed again to apply another insecticide, because it also prevents the effect of free beetle only for 4 weeks. Also, we did another trials. In this one, we tried to, because in many farmers, because this is a big problem in southern parts. So other farmers, they use this carrot more than once, maybe 3 times. And the other, they use more than 5 meals, which is the one recommended by manufacturers. So we try to look if they use more than one, the yield will be high or will be the same as if they use the ones. And if they double maybe the rate, they can get more yield or not. That is the result we try to look. And you observe, if you use gaucho and the carrot at once, the yield can be similar as if you use gaucho in the rate of twice than the one recommended, and if you apply carrot twice. Also, we did other experiments to look for the effect of mukuna, because the previous we tried to look only on chinyere, and we realized that this snake beans is not easy to get in our place, because many are available to the place where they do fishing, because this is they use to fishing. It's very poisonous. So now that's why we try to add mukuna, because this is easy to get it in our place, to see if mukuna and chinyere can perform similar, and you realize there is no difference in the yield if we use mukuna or you use chinyere. So farmers also can use mukuna to control sesame free beetle. That's it. As you see, carrots still perform better compared to other botanicals. But also it's better to use these botanicals to control free beetle than to use the feed without control. So what is waste handling conclusion? We plan to do more research and to get more advice in the setup of the research in order for us to capture more information, because the one who did this trial all are breeders, so maybe sometimes we miss other information. So, and also we plan to do on farm and to add more botanical plants in order to control these fruit beetles. We like to acknowledge ADAT for funding these studies, also NARI staff for course. Thanks.
Thanks, Happy. So do we have any questions for Happy? We've got a minute or two. I've got one question I'd quite like to know about. Is the botany, the botanical side, the taxonomy side of this? Because you refer to them in several words, but I don't think I actually... Do you know what the current name is for your snake bean? The current Latin scientific name for your snake beans?
Yes. I don't know how to pronounce, but it is. I put somewhere, I
think I saw Schwartz here somewhere.
This one.
Yeah. So, Schwartz in Madagascar. Yeah, okay. So I'm just going to use this as an opportunity to lecture everybody about taxonomy and botany. Because this is actually the only point in the talk where we see Schwartzia madagascariensis, which is in theory correct, although its current name is Bodgunia madagascariensis. Interestingly, even though it's not found in Madagascar, but that's another point. One thing I'd like to say is how important it is to get the taxonomy right and to not necessarily, as you did a little bit here, rely on common names for plants. Because if you look up snake bean on the internet, it will take you to Vigna unguiculata subspecies sesquipedalis, which is the snake bean, which is very long beans that you can eat. So I think it's very important for us to kind of, as people who are going to be leading in botanically based pest management, to get the botany right. I think it's a very important point that sometimes can be overlooked. Do we have any specific questions for Happy about the other talk? We've got one question here from John. You'll use the microphone, John, because then everyone can hear you. Thanks.
Thank you so much for a nice presentation. My question is, the mucuna that you use, is it mucuna pruriensis or another species? All right. In my country, mucuna pruriensis, you take the seeds, some people eat, and for you to eat that, you need to decant the water several times because there's a lot of what we call aerodopa. Now, when you use mucuna pruriensis, probably you need later on to do maybe a research to find out the bioaccumulation in the sesame, because you never know whether the aerodopa is accumulated in the sesame, and then it might cause another problem. So probably as a future research, you need to look at that. Thank you so much.
Okay, thanks. Even in my place, they eat this mucuna pruriensis, and they can make it boil for 12 times in order to remove that toxin.
Great, okay, thanks. We're going to move on now to Maulid. Yes, he is. I think I got that right. I should know your name perfectly by now. Maulid Watawala is going to be coming up and talking. I'm going to get his talk out right now. Maulid is going to be talking to us about the responses of two fly species to doses of Derisivitica.
Okay, good morning everyone. I'm going to present the results or part of the story about the responses of two fly species to doses of Derisivitica. This is the work that was done mostly by master students with this name, Miriam Katroba, but in association with other researchers, including Dr. Missy Malebo, who's here also. So some of the questions will be hopefully answered by him. So briefly on the background, so fruit flies are a threat to food and nutrition security because they affect both availability of dietary requirements, essential vitamins, but also the economic losses also affects access to food because farmers sell fruits so that they can buy staple foods. And more importantly, most of them are of quarantine importance, which means when you have them in a country, you lose the export markets. Now, in Africa, we have some native and exotic species. And unfortunately, the exotic ones are the most damaging. And this study focused on two exotic species, The first one called Zygrodacus cucurbitae, which was formerly called Bactrocera cucurbitae. Now, this one is a stenofagus, so it is limited to a very few families, and mainly Vitesi, but sometimes they also attack tomato, as seen from this photo. So some Sudanese can also be attacked. They are attracted to Kulua, which is a parapheromone, and it invaded Africa during the 8th century, so it has been in Africa for quite a while. And the other one is Bactrocera rosalis. It's another invasive species. The introduction is more recent. It came to Africa in 2003. But this one is polyphagous, so it attacks a wide range of fruits, including marula, as well as lucky nuts, the vegetable viana, which you can see on the photo. And this one is attracted to methyl eugenol, which is another attractant. Now, generally, the model for management of fruit flies is the same. And we say it's normally as easy as 1, 2, 3, 4. And the basic components are 1, monitoring the population, which is like the first line of defense. Then orchard sanitation, because if you lose pollen, if you leave pollen fruits on the ground, then the population will keep on increasing, because the larvae will pupate and the pupil, the adults will emerge and the cycle continues. But the more important one is sports, application of bait, which is more suppression, as well as male annihilation, which sometimes is called mass trapping or attract and kill. The tool is the same, but the concepts are different. But the model is like this, that you have to do 1, 2, 3, 4. Now, Tanzania designed a management plan for fruit flies, and part of that plan outlines some areas for further research, apart from implementation. Part of it is to search for alternatives, because you have a model, the 1, 2, 3, 4, but then you need tools for implementing that model. So you need dates, you need attractants, and you need a proper method for disposing the fruits. Now, normally we use the commercial dates, like the one that I'm showing, methyl eugenol, for example, as I said, for Bactrocera invaders, and Kulua for Zygrodacus cucurbitae. We also have dates, which we apply in sports, and the most popular one for now is GF120, or such as bait, which contains spinosad. Then you have to dispose your fruits, but this is mostly laborious, and farmers don't like it. They don't like collecting pollen fruits from the orchards. So we have to find ways of adding value to disposal methods. So like if you can make biofertilizers, fertilizers, if you can make animal feeds out of it, farmers will be more readily to accept the method. So we concentrated on the bait, not the attractants or not the disposal methods. And we looked at the most commonly applied bait in the field now, which, as I said, is GF120, which contains spinosad as well as corn molasses in it. And we thought that an ideal fruit fly bait, if you were to do something cheap and alternative, not necessarily cheap, but alternative, should contain these sources, a protein source, which could come from brewery waste yeast, which normally people used to feed chicken and stuff, or pigeons. And then we need a sugar source, and you can get that one, for example, from molasses, as well as now toxicant. And an example is Paris elliptica, which is a toxicant. So we thought that we can formulate something out of these three, so we have the protein source, the sugar source, as well as the toxicant. And we did some studies, preliminary studies, using the crude extracts, just using extracting the phytochemicals using water and soap. And these are the results that we got on incidence, which is simply percentage of infested samples. And the differences were not very much. You can see the botanical idea, because we formulated them in the IPM program, and most of these programs perform more or less the same on incidence, as well as the infestation rate, which is the number of flies that you get out of an infested fruit. And part of these were presented during the first conference on botanical pesticides in Nairobi, and part of them are presented in a recent book on fruit fly research. Now, when in Nairobi, that's where I met Dr. Malebo, and he suggested that we should move forward towards formulations. And so this is what he came up with, that let's try some different solvents and try to make formulation out of it. So we picked those 4 solvents: petroleum ether, chloromethane, methanol, and water. And we're showing their polarity indices. And then we use the normal sorting extraction method. And then finally, what we came up with were the extracts from those solvents mixed with molasses, brewery yeast, bentonite, patent, and water to make that formulation. So the results that we got are shown on the table, first on the dose response curves, and mortalities of the flies differ significantly among the formulations from the different solvents, based on different solvents, as well as among doses, which is obvious. So you had higher mortalities at higher doses, which is obvious, and you had higher mortalities as time went on, which was also obvious. So on the left, we're showing mortality curves for different extracts, and then we did some analysis of variance, so we did them two-way and over to check on the extracts based at the doses. So these are the results. And in this case, when we worked with Zubidacus cucurbitae, extracts coming from dichloromethanol gave the highest mortalities, and of course at the highest dose, which was set at 9 milligrams per liter. For Rosalis, the trends were more or less the same, but only that in this case, we got highest mortalities from the extracts that came from petroleum ether. And the highest dose, gave the highest mortality as well, and as the time went by, also the mortalities increased. And then we did some probit analysis for populations of flies that were exposed to those toxicants at various hours. And you can see that in this case, we also included the water extract that we used. Now, the data coming from, with the chemicals from water extracts gave a bit, we achieved the 50% mortalities using a much higher dose of gas compared to, for example, methanol as well as petroleum ether. So the highest value is for the water extract, which needed a much higher dose to reach the 50% mortality. And that's for Zubidacus cucurbitae. And we did the same also for Bacteria rosalis, and the trend is the same, that the extracts from water, it took longer or it took higher doses to reach a higher mortality, the 50% mortality, compared to, for example, petroleum ether or methanol. So, based on the results, we concluded that the lethal concentration 50 increased with polarity indices or polarity index of the solvent, because in the results we saw that water had a higher polarity index, and the implication is it got lower levels of phytochemicals when we use the water extracts compared to the other solvents, because then we could reach higher, a level of 50 at lower concentration. So the plans are, because first of all, we want to see that if that thing can work as a bait, whether the flies can actually come and consume the molasses or attract them to molasses, whether the flies can also be consumed into brewery-based yeast, and that works, and also to see if the combination with the toxicant can actually work and kill the flies. So the plan is to work with more refined extracts and even including some other pesticidal plants, because there is a challenge with this, because we're using the roots and with propagation that can be a problem, so we have to try some other toxicants. And then after some more work, then we can extend the work to the semi-natural conditions in the field, either in cages or something like that. So we'd like to acknowledge support of organizers of the second international conference on pesticide plants, and special thanks or personal thanks to Steve Belden and Brighton Mbumi for facilitating our travel to Zimbabwe. We thank our employers, Government of Tanzania, Sokoine University, and National Institute for Medical Research. And thank you so much.
Thank you very much about it. It's very edifying to realise that some of your research stemmed from a connection that you made at the last International Conference on Pesticides and Plants. So maybe some connections here might stimulate further work that will be presented at the third. So thank you, Matt. Do we have a couple of minutes for questions? We have one here.
Maybe just a comment.
Yes.
I think it is very important to look at different extractors. But something that we found is that acetone is by far the best extraction if you look at the compounds that are extracted. Because it mixes both with non-polar and with polar compounds. Ethanol is usually second best, but methanol is much more toxic. Acetone has got a very, very low toxicity. For microorganisms, we can understand 25%. Acetone is much less toxic to humans than ethanol. So, and it's the most wonderful thing to work with. You can leave it open and test it in that way. So I would like to make it clear for you, using acetone. Because the trouble of using dichloromethane, you use the retinol, petrol, ethane, it's more or less the same things you get here. Acetone takes a much wider range. And we've found in many, many cases, acetone is always the best extractant.
Okay, thank you so much. Because I'm more into ecology and biology, so Dr. Marego is taking that note.
That's very true. We generally favour acetone for its low toxic sort of secondary effects against the organisms that we're testing. Right, do you have a question?
You mentioned that one of the fruit fly species seems to be very aggressive, the exotic one. What's the possible reason? Could it be that it doesn't have a lot of natural enemies, like in the case of our larger grain borer storage pests, which proliferated much more in Africa when it was introduced, maybe because it didn't have any natural enemies locally. What's the story with your fruit fly?
Yeah, thank you. Because this species that was first thought to be new to science, it was named Bactocera gregis, and later on it was known to be just the same as Bactocera dorsalis from Asia. It's actually a very serious pest, even in Asia, in its native form. But what we found that when it came to Tanzania, it was very aggressive. So out of competition, it could displace the native species out of mango and so many other fruits. The fecundities are very high. You can get 300 flies from a kilo of mango, which is too much. They fly very strongly, even by wind. So it has all those competitive traits which the native species do not have, apart from having the
tickets. I think we now have a couple of farewells to make. All right.
Thanks very much to the chairs of the morning session. Let's give them this afternoon we may not have our guest of honor. We may also not have our PDC. They have to attend other agendas. So we need to just acknowledge their input into this conference. So we've got just a token of appreciation, so that they will remember about this conference. And so I will ask a few words.
Well, yes, I'd just like to reiterate what Brian said. It's very pleasing that senior members of the academic and government world will give us the time to come and hear our our stories. And we hope that your interest will continue and that perhaps at some stage in the phase of actually putting some of these scientific ideas into practice and developing real commercial opportunities and benefits for some of the smallholder farmers that are to target much of this work, but also potential to develop rather larger commercial opportunities for the business world too. So thank you both very much indeed for coming.
Thank you. So, may you come up front, please? So, token of appreciation. Thank you very much. This is please. All right, thank you very much. Well, there's gold in there, so don't lose the message. Thank you.
Lunch tickets at the back. Photograph, please.
The photograph is right at the front. So you can quickly, we don't want to lose time. We need to be here at 2 o'clock. So let's be very time conscious, otherwise we lose some of the presentations.
Better to leave your bags here, I think they will be safe.